So the although the electrophilic reagent here is usually an alkyl halide, here is tertiary butyl chloride. So it has the electrophilic fragment, alkyl part, and the nucleophilic fragment, the chloride part. Now, if you really look at the reaction at the molecular level, what is a true electrophile that react with benzene ring, okay? To give you the sigma complex. The sigma complex is the, the cationic intermediate, okay? So that, the true electrophile, after quite a little bit of study by chemists, they found that is actually carbocation. So how does a carbocation form? Is that when you add the key catalyst here, aluminum chloride. So as we discussed last class, aluminum chloride is a what kind of compound? Does anyone recall we discussed last class? If you look at aluminum chloride structure, okay, this is a Lewis structure of aluminum chloride. Look at the alumina. So if you look at the full Lewis structure, alumina has how many valence electrons around it? Around it, okay? How many valence electrons alumina has access to? Louder, please. 6, okay? So how many it wants? 8. So it has has the strong desire to get additional how many? 2. Okay, 2 is a pair of electrons. Okay, so aluminum chloride is a very, very typical Lewis acid because they want to get a pair, grab a pair of electrons, valence electrons. So aluminum chloride is very, very typical. Okay, the one of most commonly encountered strong Lewis acid. Okay? It's a strong Lewis acid. So what happens is because aluminum chloride is strong Lewis acid, so you want to grab a pair of electrons, and in the alkyl, this tertiary butyl chloride on chlorine, there are 3 lone pairs. So yeah, they make good deal. This guy is a good Lewis acid electron pair acceptor, and this guy is capable of donating electron pairs. So this electron pair donor acceptor, they form a complex. Okay? So chloride, one of chloride pair is donated to the alumina in the alumina chloride, forming this complex. And this complex then, undergo ionization process. Basically, this pair can break, goes into the chlorine, give you the tetrachloroaluminate ion. And why this reaction want to happen? Because of this tetrachloroaluminate ion is a very, very weak base. So this one is actually generally considered even weaker base than chloride itself. Okay, this one is, the chloride already pretty weak base because of in the sequence of hydrogen halides, only the fluoride is relatively strong base. All other chloride, bromide, iodides, if you learn from organic 1, they are all very weak bases. Okay? And this guy is even weaker base than chloride itself. Okay, and a very weak nucleophile. So that's why this dissociation event can happen readily. Okay, and the other reason for this association event happen readily because of stability of this carbocation. Because I hope you recall this carbocation is tertiary carbocation, and the tertiary carbocation is most stable type of conventional, let's say, conventional carbocations. Okay, so that's why this one can form. Then this one is a true electrophile that react with aromatic ring. Okay, so if you want to look at the just to help you get familiar with the process, once the tertiary carbocation forms, okay, let's look at the rate limiting step again. Just help you be familiar with the process, okay? So this pair attacks here, okay? And give you the and the pair become bonding pair between the ring and the original tertiary the electrophilic carbon on the carbocation. And then this is a rate limiting step. And this guy is a sigma complex, okay? And obviously the next step is this one, lose a pair of proton. And we could have something like the tetrachloroaluminate ion. Hold up, let me take this one away. See, you could have this chloride coming take this proton away, okay? And obviously, this one origin have negative charge, then go to here, and then give you the final product, aluminum chloride as a catalyst recovered, HCl, then plus the the final product, the alkylated benzene. So as far as the reaction name goes, all those alkylation reaction of benzene, if carbocation is involved as the true electrophile, those reactions can be called a Friedel-Crafts alkylation reaction. Although the original Friedel-Crafts alkylation reaction use aluminum chloride as a catalyst, okay? But generalize the Friedel-Crafts reaction, including any reactions that involves carbocation, okay? As the electrophile react with the aromatic ring is called Friedel-Crafts alkylation reaction. So technically the carbocations, although original Friedel-Crafts reaction carbocation is formed from the alkyl halide and aluminum chloride, but more general Friedel-Crafts reaction can generate the carbocation, the true electrophile, by other means. We're going to talk about later. Okay? So the one thing is because of this Friedel-Crafts reaction, involve carbocation as a true intermediate. So the same limitation will apply as far as what kind of carbocation can be involved. If you recall from general chemistry 1, okay, what kind of carbocation cannot be involved? Primary, very good, and even worse one, the methyl one. Okay, but generally those very unstable carbocations generally are very unlikely to be involved in this reaction. Okay, so now if you recall what you learned, in the organic one, carbocations actually can have, can participate in quite a few reactions, generally 3 types of reactions. First, react with nucleophiles. That's what the major reaction we have seen here. The carbocations, okay, can react with nucleophile. Here, the benzene ring is acting as a nucleophile. Okay, carbocations can react with nucleophiles. Okay, and the carbocations can also, lose a proton from beta carbon to form alkene. That's the elimination reaction. So that's actually the type of reactions we have seen here. This in the elimination step. So this is also a carbocation, right? but this carbocation can lose a beta proton, okay, become alkene. Here we restore the aromaticity, but if you look at locally, this part is elimination reaction because it loses beta proton, forming an alkene locally, okay. And but also, I hope you recall the carbocation could rearrange, from a less stable one to a more stable carbocation. So this is the reason why if you use, say, the primary alkyl halide as the electrophilic reagent, and let this primary alkyl halide react with benzene using aluminum chloride as a catalyst, you will not get alkylated benzene with the primary alkyl group. Okay, so here you see this guy is a primary, okay, alkyl group. You would expect, without thinking about rearrangement, you probably might be thinking about, okay, because this is a primary alkyl halide, so I should be expecting this product, okay? Right? You should be expecting this because that's the, this alkyl group, because this should be electrophilic carbon, okay? You should be expecting this, but what you be getting is this one. Why? Because, keep in mind, this one, as far as mechanism goes, this one need to react with the catalyst first, okay? This is a Lewis acid, give you a complex, okay? And this is the complex, okay? And when this complex, undergoes the dissociation reaction, producing the true electrophile, the carbocation, it won't form the, you so-called expected primary carbocation, because as we know, the primary carbocation is so unstable. That means based on the hormone deposit, when a carbocation is very unstable, its formation activation energy is very high. So just thinking about it, okay. So think about the carbocation formation reaction. So if it's a primary carbocation, is like this, okay. And now if it's rearranged into a tertiary carbocation, the stability is like this. So this is the red pathway is like the one we're showing here. So this complex, okay, will undergo a hydride shift. So what happens is, it's happening in one step. The hydrogen connect to the tertiary carbon together with a pair of electrons here. That's important. This pair of electrons, okay, under the hydrogen will move to this primary carbon. At the same time, when this pair of electrons goes to the chlorine, same time. So this move to here, when this one move to here, and this give you this hydride shift give you a tertiary carbocation. Although technically, this shift involve two electron transfer event happen at the same time. So probability-wise, could be, not super favorable, okay? But because of it give you a much more stable carbocation, so this carbocation formation can have a potential energy diagram like the red one, okay? If you directly form a primary carbocation, then it would be something like, okay, something, if you directly form primary carbocation, okay, this will be black pathway, okay, because the primary carbocation, okay, is so much less stable than the tertiary carbocation. So this is a primary carbocation, okay, this is a tertiary carbocation. So its formation rate, okay, is a lot. See, because this is activation. So the black pathway has a much higher activation energy, okay? much higher activation energy than the red pathway. So that makes the formation of the primary carbocation, okay, is a lot slower than the corresponding tertiary carbocation. Okay, so that's why you actually if you have a primary alkyl halide, you let it undergo Friedel-Crafts reaction, you will undergo rearrangement, give you either secondary or tertiary, the product. Okay, because the complex first step is alkyl halide form a complex with aluminum chloride. Then this complex, if it's primary, you will at least undergo a shift, give you secondary carbocation. Okay, at least. Okay, you will not give you a primary carbocation. So as I mentioned, all the alkylation reaction where the carbocation serve as a true electrophile, they are called Friedel-Crafts reaction. And the carbocation can be created by other means. And if you recall from organic 1, there are quite a few ways to form carbocation. One of the ways is the protonation of alcohol, followed by dissociation of water. The other way is the protonation of alkenes. Okay, so here just one example. If you mix with benzene with cyclohexene, then add a bit of sulfuric acid as a catalyst. So this sulfuric acid can protonate the alkene, okay, and give you the carbocation. So basically, if you have this one, and it's important using sulfuric acid, not hydrogen chloride, because I hope you recall from organic 1, sulfuric acid is an acid where the conjugate base of the acid is a very weak nucleophile. Okay, so this is important. So basically, in the first step is this will give you the hydrogen sulfate ion, and then the plus the carbocation. Okay, and this one is a true electrophile. Okay, for the same reason, this reaction will give you the alkylation product, because the tertiary butanol, if you recall what you learned in organic 1, can be protonated by a strong acid like a sulfuric acid. Okay, give you the protonated alcohol plus obviously the sulfuric acid, become hydrogen sulfate ion. Then this protonated alcohol can undergo the ionization, give you the tertiary butyl cation. Okay, and this tertiary butyl carbocation will be serving as a true electrophile react with benzene. And besides the alkyl halide can be used as electrophilic reagent. There's another class, a class of the halides called acyl, halide. So this kind of, the halide basically features a carbon that a carbonyl carbon. So the this group, okay, this group is a carbonyl group. CO double bond is a carbonyl group, and this carbon we call carbonyl carbon. The carbonyl carbon also connect to halogen. Usually is a chloride. So this class of compound we call those compounds with this group, carbonyl carbon connect to the chlorine, we call acyl chloride. So ACYL, acyl chloride. Okay? And in acyl chloride, this carbon, okay, is highly electrophilic. Is actually even more electrophilic than the alkyl halide. So this, let's see if you compare to this compound, okay, with this compound. So in both this compound, the carbon connect to the chlorine is the electrophilic carbon, but this carbon is substantially more electrophilic than this carbon. The reason is because of this carbon. On this carbon, you have much greater share of positive charge, because of here the positive charge mostly come from the electron withdrawing power of a single chlorine atom. But this carbon, a positive charge, come from electron withdrawing power of chlorine and the electron withdrawing power of even more electronegative oxygen, which is double bonded even. So make this carbon extremely electrophilic. Okay. So no wonder this one also can serve as the electrophilic reagent, react with benzene. And typically you also will need to use aluminum chloride as a catalyst. So the net reaction is the carbonyl carbon. It's important, the carbonyl carbon, the one connected to oxygen. Carbonyl carbon will be bound to the aromatic ring. Okay. So in this reaction, the electrophile is called acylium ion. It's not conventional alkyl carbocation, called acylium ion. Okay, so it's basically can consider this acyl chloride just break this pair of electrons, go to chlorine, it can give you the acylium ion cation. Okay. And the exact formation process we're going to talk about later. Okay? But what I want to emphasize here is acylium cation is substantially more stable than conventional alkyl carbocation. Acylium cation, where the positive charge sits on the carbonyl carbon, is even more stable than a tertiary carbocation. Why that's the case? Look at it, okay? So if you have a positive charge carbon here, right? And this carbon has 6 valence electrons, okay? And you can actually write the other resonance form by moving a pair on the oxygen, okay? Lone pair, become bonding pair, become carbon and oxygen, give you carbon-oxygen triple bond. So in this way, in this right side resonance form, every carbon, every atom has octet. So here oxygen already has octet, right? Now the carbon also has octet, because how many valence electrons do you have on the carbon? How many valence electrons the carbon has access to? Look at this here. 1, 2, 3, 4, 8 valence electrons, okay? The oxygen also has access to 8 valence electrons. So every atom satisfies octet. So because of the existence of this resonance form, that makes this acylium carbocation more stable than conventional, even tertiary carbocation. So what is the consequence of having this resonance form? Acylium ion, they do not undergo rearrangement whatsoever. Okay, do not, because this is already more stable than a conventional tertiary carbocation. What's good if they want to rearrange to tertiary? Become not stable. They don't want to. There's no motivation, right? no motivation whatsoever. So this is the important difference between the acylium ion and the conventional alkyl carbocation. If you have a conventional alkyl carbocation, if it's primary or secondary, they may undergo a rearrangement to give you a more stable tertiary carbocation. They may, okay? But this one will never, because it's already most stable type of carbocation. Okay, a big difference. Okay. So here just show you how the acylium carbocation forms. Okay, first, you know, the acyl chloride forms the complex aluminum chloride in the same way as the you know, the alkyl halide, exactly the same. Okay, then the same way this one, this pair of electron breaks, goes to chlorine, give you the tetrachloroaluminate ion. This is highly stable, you know, the anion, and leaves the acylium cation. And this acylium cation is very stable because you can write the other resonance form. You know, I'm gonna just draw it here again to emphasize its stability. Because of that form exists, okay, makes the red form, because the lower form exists, okay, this acylium carbocation will never undergo rearrangement, okay, because it's already more stable carbocation, even more stable than tertiary. No motivation to rearrange. Okay, so this is a big difference. So the if you look at the product, okay, the Friedel-Crafts alkylation reaction product is a aromatic ring connect to the carbonyl group, then connect to rest of the, you know, the basic the alkyl group. So this compound we call it is aromatic ketone. Okay, is what is a ketone? Ketone is a compound with a carbonyl group. Both sides connect to a hydrocarbon group, means a carbon-based group. Okay, so this one left side is a carbon-based group, right side also carbon-based group. So this is a ketone, and because one of the hydrocarbon group is aromatic group, so it's because aromatic ketone. So the in terms of the, you know, the addition rate limiting addition step is pretty much the same for all the electrophilic aromatic substitution reaction. The aromatic the benzene ring acts as a nucleophile, donate a pair of pi electrons, attack the electrophilic carbon, and give you the sigma complex, which is a cationic species. It's a allylic carbocation, and in this step, aromaticity is destroyed, so it's highly endothermic and slow rate limiting. Okay, the next step, you know, the reasonable base come in to remove a beta proton and restore the aromaticity, give you an aromatic ketone. Okay, and the how the acyl chloride is prepared, you know, in a laboratory is typically almost always acyl chloride is prepared by a carboxylic acid. So what is a carboxylic acid? Carboxylic acid is a compound that features a carboxyl group, is COO, a carbonyl. This is a carbonyl group. Carbonyl group one side connect to the carbonyl carbon bound to OH group. So this whole group, we call it this whole group, okay, we call it carboxyl group. Okay, so any compound has a carboxyl group, we call it carboxylic acid. Okay, so this group we call carboxyl group. This first time probably seeing it, but later you will see it much more frequently. This group called carboxyl group, and a compound has a carboxyl group called carboxylic acid. Okay, and one most commonly known carboxylic acid is, can anyone tell me one of carboxylic one example? Every one of you must have eaten it. Every one of you, yeah.
Acetic acid?
Yes, very good. Okay, acetic acid. That's the active component in vinegar. Okay, so I'm pretty sure every one of you have Either, you know, I mean, when I was young, I was a kid, I like to drink it actually. But you know, at least if probably if you like to drink it, at least it's, you know, you use it in your meal, whatever. Okay. Anyway, so the when you have a carboxylic acid, you can let it react with the SOCl2 called thionyl chloride, and this reaction can basically replace OH group with Cl. This reaction, the driving force is actually because of thionyl chloride is a highly reactive compound. By after the reaction, thionyl chloride become less reactive sulfur dioxide and HCl. That's the major driving force. Okay, thionyl chloride itself is a highly reactive compound. So this is how the acyl chloride form. And besides acyl chloride, okay, so one reason acyl chloride can, you know, the is often used for this reaction is because acyl chloride, after mixing with aluminum chloride, can give us the true electrophile, ethylene cation. Okay, and so you actually could have using other reagents as long as that reagent can react with aluminum chloride, give you the ethylene cation. This one, okay? So you can have the same Friedel-Crafts acylation reaction. As long as that thing can react with aluminum chloride, give you the ethylene cation, okay? Because this one is a true electrophile, okay? So that's why you also could use the called, you know, this kind of compound, okay, we call it anhydride. So what's anhydride? Is basically two carbonyl groups share the same oxygen. So you can consider this whole part later can come off as ethylene cation. Okay, so this part, the right side part, is the, you know, the nucleophilic part. So this part can combine with the aluminum chloride. Okay, then, you know, they form complex. Later release the complex can release the ethylene cation as a true electrophile, and the anhydride also can serve as the you know, the source of ethylene cation. So let's just give you one example for this, one more example for this type of reaction. So let's say we have a benzene ring. This is a faster way of showing benzene ring. Okay, so knowing that it's going to be electrophilic aromatic substitution reaction, so you know the how you can develop ability to what is electrophilic fragment in the reagent. The left side part is electrophilic reagent, okay, electrophilic fragment, and the chloride is a nucleophilic one. So this one is nucleophilic one with a pair of electrons. Okay, so then it's important that you have to connect the electrophilic carbon to the ring. So it has to be the carbonyl carbon, okay, to the ring. Then the rest of the molecule just gets carried over into the product. And then you know, the hydrogen obviously you know, the proton aromatic ring going to combine with the nucleophilic chloride, hydrogen chloride. Now, having learned those two, you know, the Friedel-Crafts type of reactions, let's discuss about, you know, the synthesis of the alkyl benzenes, especially primary alkyl benzenes. Okay, so let's say if you are given a task of synthesizing this compound, start from the unsubstituted parent benzene. Okay, so the one possible way for a student who just learned the Friedel-Crafts reactions, okay, maybe I could directly just you know, because I know that I need to install this thing, okay, alkyl group onto the benzene ring, right? So maybe I could just using the corresponding alkyl halide. the primary one carry out a Friedel-Crafts alkylation reaction. Okay? The question is, will this reaction work? Very good. I see quite a few shaking head, but why? If you want this to work, you need to form a primary carbocation. Okay, and as we know, primary carbocation formation is impractical because it will rearrange to something else. That's the reason. Okay, so if you really do that, okay, you know is basically you're gonna have, this thing gonna form. No question. Okay, this gonna form. Okay, but when it ionizes, forms carbocation, this thing gonna happen. Okay, this thing will be happening. So you're gonna have a secondary carbocation. Okay, and the secondary carbocation react with benzene will give you so that will be the product. Okay, so if you directly take this one, you get this product. Won't work. Okay, because primary carbocation the formation is just impractical. You will find a way to rearrange to something else. Okay, so that means direct alkylation won't work. So how do you do that? So we know that Friedel-Crafts alkylation does not involve a rearrangement. So so technically you could directly get the primary carbon attached to the aromatic ring. So in that particular case, you could, using this guy, instead of alkyl halide, I use this one, okay? And then aluminum chloride, okay? Then I could get to this guy as this one, okay? So the carbon skeleton on the aromatic ring looks okay, okay? It's straight, primary, right? But the problem is, what I wanted is this CH2 here, okay? But here I get a carbonyl group there, okay? So I have to do, something to convert this carbonyl group, okay, into a CH2, okay? So that you need a reduction reaction. So the general, this basically, this whole scheme shows your general strategy if you are asked to synthesize the primary alkyl benzene. You need, using first go through alkylation reaction, you can convert to you have a aromatic ketone where you have a primary carbon connect to the aromatic ring. Then you have to find a way to convert the carbonyl group to a CH2 group. And that is a reduction reaction. So there are two reduction reactions we can use. One is to take the ketone, let it react with zinc amalgam. Okay, it's basically zinc mercury alloy. So this zinc amalgam is basically you treat the zinc surface with mercury. Okay, so in the presence of hydrogen chloride acidic environment, then the carbonyl group can be reduced to CH2. And in this reaction, zinc is the active reducing agent, and and HCl serves as a source of proton. It's not really, hydrogen gas is not directly involved. Okay? So this reduction called Clemmensen reduction. So the mechanism actually quite complicated. So I don't think it was a time to go through it because we would not need the mechanism in the later part of the course. So I would just suggest you to memorize that, the zinc mercury alloy can reduce carbonyl group into CH2. So all those parts, no change. This part, no change. Only carbonyl group is reduced to the CH2 here. Okay. So and this reaction, because it has hydrochloric acid, is pretty acidic. So this reaction works best, when if you look at if there are other groups, functional groups on the aromatic ring. In order for this reaction to work, those other functional groups on the aromatic ring must be stable on the acidic environment, means it will not be destroyed by acid. But if for typical conditions like a reaction shown in here, this certainly works because all those just hydrogens, so they are very stable. Okay. Now the other way to do the reduction is called Wolff-Kishner reduction. So this one is you're going to using hydrazine. Hydrazine is NH2, two NH group connect together called hydrazine. H2N, these two N bond together, okay? Then you have the basically this is a structure. Like it's similar to ammonia. You can consider two ammonia, the molecule bound together on their nitrogen atom. Okay, so this is called hydrazine. Hydrazine is a good reducing agent, and then also need a KOH, and you need using a high boiling point solvent, and the triethylene glycol is a commonly used solvent for that purpose, and this reaction requires a high temperature. So as you can see, this reaction involves a strong base. So this reaction is suitable for those reagents or those compounds where those rest of the functional groups, if you have on the ring, will be stable on the basic conditions. Okay. So in real world, probably in the if in the case you will be encountering in the exams, either of those methods will work. Either one will work, because likely we will not be really dealing with those groups, that are not stable on acidic or not stable under the basic conditions. So you don't need to worry. You probably can use any of those methods. Okay, any of those methods. But if you really need to do this reduction in a real world, let's say if you're doing a project, you are synthesizing a complicated reaction, a complicated compound involves introducing a primary alkyl group on aromatic ring, then you really need to inspect the rest of the molecule, to choose a best method, whether the Clemmensen reduction or Wolff-Kishner reduction. And just give you one example, to synthesize. You're probably gonna see one in the next exam. Let's say if you're asked to synthesize, this guy, okay? Start from benzene as starting material, okay? So obviously if you directly do this with alkylation, you would need this one to do the reaction, okay? And if you take this approach, it certainly will fail, because we know that in this reaction you will see carbocation rearrangement. So you will not be getting the product you wanted. Instead, you will be getting this one as your product. Okay, so this one won't work. So how do you do that? You will need to go through the alkylation path, like here. Okay, alumina chloride. Okay, then you get this alkylation product. Then you can do the Clemmensen reduction. Why the reason you go through alkylation is because in this the Friedel-Crafts alkylation reaction, There's no rearrangement. You can, the faithfully, the keep the structure of LQ group in the Friedel-Crafts product. Okay, then you can use reducing agent to reduce carbonyl group to CH2. Yes.
I thought not to use water in between those. Like when you write the steps, when you write like AlCl3, do you put water in between?
No, we don't put
because it's like reactive. How reactive are they? So
well,
do you use water?
We don't use water at all. No. See the all those reactions. In second step you may need you use water because HCl is it's generally gas. Water is involved, but in first step there's no water.
So when you write out, do first step is AlCl3 and second step is water and third is
no water. Here no water.
Even though it's reactive,
it's reactive, but actually this reaction you have to be very careful to avoid water because AlCl2 can react with water. Okay. We don't use water. Let's say in the first step, above the dash line, no water involved. Because of the Clemmensen reduction, HCl involves the water. Because of the HCl, you get the commercially as a water solution, hydrochloric acid have water there. But in first step, you have to carefully avoid water because you have water going to destroy aluminum chloride. Water will react with aluminum chloride, will destroy it.
So only 2 steps?
Yeah, 2 steps, 2 experimental steps. I'm not talking about mechanisms. Mechanism is separate because in the first experimental step involve multiple steps. First is catalyst react with the chloride, then create ethylene cation. That's 2 steps already. The ethylene cation undergo addition, another step, that's rate limiting step, then elimination kind of step. So I'm talking about the experimental steps. The first step, no water. You have to be very careful to avoid water because aluminum chloride can be killed by water. As a matter of fact, if you want to use aluminum chloride catalyst, you have to carefully seal seal your container. If you don't seal it well, after a few months, aluminum chloride becomes useless as catalyst. All right, let's have a break. Maybe let's 5-6 minutes.